So the Schrodinger equation we are going to discuss now, and which is basically given by the Erwin Schrodinger uh, in 1926. So right now we'll discuss the Schrodinger equation of time-dependent form. Schrodinger equation basically cannot be derived from any other basic principles of physics. So because it is a basic principle in itself, so no one can derive the Schrodinger equation. The form of the Schrodinger equation was given by the Erwin Schrodinger directly through his intuition. He just write the differential equation as a function of psi, and that is the Schrodinger equation. So you cannot derive the Schrodinger equation because it's a basic principle itself, like the Newton's second law of motion, F is equal to ma. It's a basic principle, basic law of the Newtonian mechanics. You cannot drive F is equal to ma. You just write F is equal to ma. In the same way, the Schrodinger equation is the basic principle, a basic law of the Schrodinger quantum mechanics. You cannot derive it from anything else. So Schrodinger equation is the fundamental equation of quantum mechanics in the same sense that the second law of the motion is the fundamental equation of the Newtonian mechanics. So Schrodinger equation is a wave equation in the variable psi. So let's suppose that we write the wave function of a free particle. Wave function of a free particle. This is psi equal to a exponential I over h cross et minus px. So this expression basically describes a free particle or unrestricted particle at which no force is acting and whose total energy is E is its total energy and P is its momentum, and this particle is moving in positive x direction. Okay, so this particle is moving in positive x direction. Positive x direction. Fine. So this expression for the wave function psi is correct only for a free moving particle. Okay, but what we are interested in, we are interested in a situation where the motion of the particle is subjected to various restrictions. That means the particle is subjected to certain kind of force. Then what will be the expression for the wave function? For example, like if an electron is bound to an atom around the nucleus by electric field. The nucleus is a positive charge and the electron is negatively charged. So the electron is revolving around the nucleus within an atom, and which is bounded by the electric field of its nucleus. So the electron is not free, and it is subjected by the restriction, which is the electric field of its nucleus. So what we must now do is to obtain the fundamental differential equation for psi. So if once we have a fundamental differential equation of psi, which is a Schrodinger equation, we can solve that Schrodinger equation to get the form of psi in a specific situation, depending upon what kind of restriction is there on that particle. So as I told you that the Schrodinger equation, or which is basically the fundamental differential equation as a function of psi, for psi, we cannot derive it. We can just write it. We can postulate it. So what? So let's not say to derive it. That is one of the way to how to get some differential equation. So we will not say that we are deriving the differential equation. Okay, we're just doing some mathematical thing. So if I differentiate this psi with respect to x, so you know how to differentiate it. I differentiate with del psi by del x once, so I can write a e minus I over h cross, and then et minus px, and then differential will give you uh, ip over h cross. Okay, and then if I double differentiate it, d2 psi over dx square, so this will give us, because a minus I over h cross et minus px, and then ip over h cross, and again ip over h cross. So this is basically I square, this is minus p square by h cross square, a e I over h cross et minus px. So this is nothing but minus p square by h cross, and this is my psi, because this is equivalent to my psi, or we can write it as p square psi is equal to minus h cross del 2 psi over del x square. Okay, so this is one equation we get by differentiating uh, psi with respect to x. So if I differentiate with respect to time, del psi by del t, what we get is a e to the power I over h cross. This is et minus px, and then this is multiplied by minus ie by h cross. So this will be basically, uh, because this is um, ie by h psi, so why they have written ih by psi, this will be minus I e by h psi. Okay, so I can write it del e psi equal to uh, this is minus h cross by I, and then del over del t of psi. Okay, so this is another set of equation when we differentiate with respect to time. Okay, now uh, for a particle, say for a particle whose velocity is much less than c, that is a non-relativistic particle. For a non-relativistic particle, we know that the total energy of this particle is written as total energy of the particle E equal to uh, P square by twice m. This is the kinetic energy plus the potential energy U. So because the particle is moving in x directions, the potential energy is depending upon x and t. So it's the kinetic energy part plus the potential energy part. So kinetic energy plus the potential energy part. This is the total energy of a particle, which is non-reducing particle, whose velocity is much less than c. So if I multiply it both side by psi, I can write E psi is equal to p square by twice m psi plus u, sorry, u xt psi. Fine. Now since I have the value of E psi here, and also we have value of P psi here, if I put these two value in this equation, what I get is like uh, this is I h cross del t of psi is equal to minus h cross by twice m del square by del x square psi plus u xt psi. This is if I take I equal to minus 1 by I. So that's why we can write this is IH cross here by del psi by del t. So this equation is time dependent form of the Schrodinger equation because time is there. This is time dependent form of the Schrodinger equation in one dimension, because I'm just using x here in one dimension for a free particle which is non-relativistic. Okay, so if I try to write in 3 dimension, we can write this equation as uh, for 3 dimension, we can write this equation as I h cross del t over psi is equal to minus h cross by twice m, and then we have del squared by del x square plus del square by del y square and del square by del z square psi, and then I have u x y z and psi. This is equation in 3 dimension for a free particle. So this is time dependent uh, time dependent form of Schrodinger equation for a free particle, free non-relativistic particle, or say three-dimensional time dependent Schrodinger equation for a free particle. So this equation, this is not a derivation for the Schrodinger time dependent form of the Schrodinger equation for a free particle, but it's just a mathematical thing to just to understand. So if someone asks you that derive a time dependent form of the Schrodinger equation, this is absurd. We cannot derive the Schrodinger equation because it's a basic principle. It's a physical principle of the quantum mechanics. You cannot derive it. Okay. So since this is Schrodinger equation, uh, which we obtained here using the wave function of a free moving particle. When I say the free moving particle, in that sense, when I say free moving particle, that means I have put this potential, which is u say xyz, potential is constant. When I talking about the potential, because the potential is related with the force uh, which is acting on the particle. So if the potential is constant, then that is the no force is acting on the particle. Okay, so particle is free, there is no restriction. But we need a situation also where uh, there's some kind of arbitrary forces are acting in the space and time on that particle. So if my xyz is not constant, it depends upon, it's not constant. Okay, then what will happen? So in such kind of situation, what actually we do in quantum mechanics is that uh, uh, we actually mm, we actually postulate a Schrodinger equation. What we do, we postulate Schrodinger equation. And once we postulate Schrodinger equation, that means we write the differential equation in terms of psi, and then what we do, we solve it. We solve it for different situations. When I'm saying different situation, that means different kind of different arbitrary forces acting on the system. And once we solve it, we get the expression for psi, and once we get psi, we can find out the mod square psi, and then we can find certain properties. So after that, we compare it, we compare the results with experiment, with experiments. And if it agrees, if the result is agrees with the experiment, so that means postulate and the Schrodinger equation is valid. Postulates and the Schrodinger equation is valid. And if disagree, and if it disagrees, then what we do, we discard the postulate, we discard the postulates through which we have written the Schrodinger equation, and do some other approach and go for some other approach. So it's quite simple. Therefore, the one important thing is that the Schrodinger equation cannot be derived from other principles of physics, because it is a basic principle in itself. And this is one of the form of the Schrodinger equation. This is time dependent form of the Schrodinger equation for a free non-relativistic particle. And if the particle is not free, restricted under certain force, so what what happens is the restriction comes in the potential, and depending upon that potential, we postulate our Schrodinger equation, solve it for different situations. Different situations means for different potentials, and compare our results with experiment. So if it agrees, my postulates leading to this potential is correct, or if it's not, then we try to postulate another differential equation, or we go for some other approach. This is the way we do or deal with physical system in the quantum mechanics. Now we will discuss the stationary states. Uh, stationary stationary states in quantum mechanics. Stationary states in quantum mechanics is nothing but simple is a simple and useful solution of Schrodinger equation. Okay, so stationary states are basically simple and useful solution of the Schrodinger equation. Stationary here doesn't mean which is not statistic. It's a kind of dynamical state, but the things are not changing in that state. Things are moving, but they are independent of time. They are not changing. So we can define a stationary state basically as a stationary state has factorized space and time dependence. That means if I write a state which is a stationary, for example, is psi. This is my stationary state, psi xt, and this is written as a factorized form. This is one, uh, say, gt, time dependent wave state, and then I have a psi, which is space dependent part. So a stationary state has a factorized space and time dependence. What it actually means is that this has a time dependence. The state itself has a time dependence in it, but the observable, which are time independent, have no time dependence in their expectation values. So the time independent observables time independent observables have no time dependence in their expectation value. What does it mean? That if I make a large number of copy of such state and try to measure experimentally some observables at the same time, then the expectation value of that observable is time independent. Okay, so when I say that stationary state are the simple and usual solution of the Schrodinger equation. Okay, so this is basically a solution of some Schrodinger equation. So let's start with the Schrodinger equation. We're just writing this uh, IH cross. If you remember the Schrodinger equation, this is IH cross del by del t. I can write psi xt is equal to minus h square by twice m del square by del x square plus say u x, and then I have psi xt. For this I can write at h psi xt, because this h is nothing but the Hamiltonian operator. This h is Hamiltonian operator, known as the Hamiltonian operator, which is nothing but this, the whole thing in bracket. This is an operator, and this can be represented as this Hamiltonian operator. Okay, so here one thing you must notice, that in the potential u, there is no time dependence. So in great many situations, the potential energy of a particle does not depends on time explicitly. Okay, explicitly there is no time dependence. That means the forces that are acting on the particle doesn't have any time dependence on it, and therefore the potential u vary with the position of the particle only. Okay, so when this is true, so the total Schrodinger equation may be simplified by removing all the reference to the time. Okay, so simply by when the potential is explicitly not time dependent, then there is this procedure we can totally remove all the references to t which are in the Schrodinger equation. Fine. So this will ultimately lead us to a steady state form of the Schrodinger equation, and we will discuss it what steady state means. So now this is my Schrodinger equation, and if I put the value of psi xt from here, that is the time dependent part and the space part in this equation, uh, what I will get is like IH cross. I can put psi space dependent part outside. This will be del t, and this will be gt, and this is equal to uh, I can write it like let's write it gt, and this is h and psi x. Okay, because all the things which are in Hamiltonian operator are time dependent. Fine, so I can write gt and h psi t. Now let's divide whole thing by the wave function psi xt. Okay, so divide both sides by psi xt. Okay, Psi xt means that means gt and psi x both sides. So what will happen? So this becomes IH cross, uh, psi will cancel out. I will have 1 by gt, and then del lt of gt, and this will be equal to 1 upon psi x and factorial psi x. Okay, now you can see that the right hand side, this is the left hand side and the right hand side. The left hand side is totally time dependent, and the right hand side of this equation is totally space dependent. So it is not possible that in equation the left hand side is time dependent and the right hand side is space dependent and they are equal. This is not meaningful. So this is meaningful only when these are equal to, they are not something, they are just a number, and these number are basically equal to a constant, and this constant is written as the E, which is a real constant with units of energy. Why unit of energy? Because this, so this psi x with psi x will cancel out, and H is a Hamiltonian operator which has a unit of energy, because H is a Hamiltonian operator and this is Hamiltonian operator, and this is kinetic energy and this is potential energy. So H is having a unit of energy. Similarly here what I have is G will cancel out, and what I have is H cross and then time. Okay, H cross and time. What is H cross by time? What is H cross by time? This is 1 by t is H cross is frequency, and this is nothing but the energy. So the left hand side and right hand side is both having a dimension or a unit of energy. That's why this constant has to be some constant, and its unit has to be energy and just a real constant. Fine. So now let's take one by one. If I put I first part left hand side, and this is say I H cross d dt of gt, I can write it as E gt, and this gives me that gt is nothing but some constant c and e to the power minus I e t by h cross. Okay, so this is the solution for this part, which is very easy. So the second part is slightly tricky, which is h psi is equal to e psi. This is h psi is equal to e psi. Okay, and so we can write it minus h square by twice m. This is d square by dx square plus ux, and then I have psi x equal to e psi x. So this is the Schrodinger equation. Either this or this, these two are same. This is the Schrodinger equation, which is known as the time independent Schrodinger equation. And when we solve this equation, we get the expression for this psi, and we have expression for the g time dependence. So we can write the expression for the stationary state, and that I can write as psi xt equal to some c times psi x e to the power minus I e t by h cross. This is what is my stationary state. So a stationary state psi is a state when the Hamiltonian times the wave function is equal to the constant, and that is the energy times the wave function. So write h psi, this is my Hamiltonian, h psi xt is e psi xt. So the stationary state is a state psi when we write the Hamiltonian times this is state psi, and then it equals to a constant, which is the energy times the wave functions. So this is my stationary state, and the equation, the Schrodinger equation, which defines the stationary state, is called the time independent Schrodinger equation. This is time independent Schrodinger equation, or we can write this as minus h squared by twice m. This is as we write del squared by del x squared plus ux, and then I have psi is equal to e psi. So I can write it as del square del x square plus twice m by h cross square and e minus u psi equal to 0. This is one dimensional, and if we write a three-dimensional, so we can write is as del square del x square, and this is psi here, psi plus del square del y square psi plus del square Lz square psi plus twice m by h cross square e minus u psi equal to 0. So this is the time independent Schrodinger equation, or also known as the steady state form of the Schrodinger equation, also known as the steady state form of the Schrodinger equation. And what else? This is also we can say that let me find it as the stationary state we can define as also as uh, a stationary state is a quantum state uh, in which all the observable in which all the observables, I think you know this, whether energy, momentum, position, velocity, linear momentum, angular momentum, whatever, all the observables are independent of time. Independent of time. It is also known as the eigenvector of of the Hamiltonian of the Hamiltonian. H. All the state correspond to a single definite energy, and that's called the eigenvalues. And the corresponding state with a single definite energy, known as the eigenvalues. Eigenvalues. I think this is okay for the stationary state. And also you know what is the time independent Schrodinger equation, form of time independent Schrodinger equation. This is time independent Schrodinger equation, either this form or this is one-dimensional form, and this is three-dimensional form, time independent or the steady state form of the Schrodinger equation. And you know this, what it means by a stationary state.